Great. So I'd like to thank the organizers for giving me the opportunity to talk about solar power, and also Douglas, our chair, for the very kind introduction. The title of my talk is Solar Power Materials, but I would like to clarify that by solar power, I am referring here to solar electricity, photovoltaics. You also have solar chemical as well as solar thermal, which are promising routes for energy generation, but in this talk I will be covering exclusively electricity generation using solar energy. So the first session we had in the morning illustrated quite nicely the effect of human activity on the climate and all the deleterious effects that we're doing in terms of CO2 generation and increased global temperatures. So renewable energy is really a key strategy to minimize the adverse effects of human activities on climate change. One criticism you could level at solar electricity or photovoltaics is that in the UK, where we do not have as much solar radiation as, for example, Mediterranean climates, the energy that you get out of solar would be perhaps limited compared to other renewable energy sources. So I want to first address that issue, and I want to address it using this graph, which shows what is called the levelized cost of electricity. Levelized cost is a means by which we compare different electricity generating technologies. So it takes into account the capital cost for setting up the infrastructure as well as operational cost. This is levelized costs of electricity for Germany. And I selected Germany because Germany has a similar solar irradiation level compared to the south of England. So it is comparing like for like somewhat. The yellow boxes that you see here are the levelized costs of electricity for solar. So you have on the left-hand side, you have small-scale PV rooftops going all the way to large-scale utility power generation. You can see that the levelized cost of electricity for solar PV is comparable to, for example, onshore wind as well as offshore, and also comparable to, for example, coal. So despite the fact that we do not have the same levels of solar radiation compared to, for example, Asian or Mediterranean countries, it is fair to say that solar electricity can still be a very important part of our energy mix. As Douglas pointed out to you, today, the UK national grid is generating some 20% of its energy from solar electricity, 5% is coming from wind, and something like 50% is coming from fossil fuel. So solar electricity is an important part of the renewable energy mix, and that is reflected in the installed capacity. This is the global installed capacity as a function of year. So you can see that year on year, you have an increase of something like 100 gigawatt of solar electricity. The yellow bars represent solar electricity and the blue represents wind electricity. So year on year, you are having something like 100 gigawatts new installation capacity that is mainly driven since 2005 by China. The previous leaders were Europe, Japan, and the US, but now that China has far exceeded those countries. And by in 2019, there was something like over 600 gigawatts of solar installed capacity. So clearly, it's a very remarkable progress, but the COP26, upcoming COP26 conference has highlighted the fact that we need to be going even faster. So the question then comes about is there any headroom to improve the cost of solar photovoltaics so that it could become more commonplace? To answer that question, we need to understand what is happening. So at a very simple level, a solar photovoltaic takes energy from the sun and converts it to electricity. Okay, so you need some kind of solar material to absorb the sunlight and convert it to electricity. At the moment, 95% of photovoltaic modules are based on silicon. Now, from a materials point of view, silicon is a rather poor choice of material because it is a weak light absorber. In the physics community, we say that silicon has an indirect band gap. That's the technical term. We don't need to worry too much about it. But the consequence of this weak light absorption is that you need larger material volumes to absorb the light. So in the case of your typical solar panel, the thickness of your silicon is something like 1/10 of a millimeter. And because it is such a weak light absorber and you need large material volumes, what it means is that the silicon we use needs to be purified to extremely good purity levels in order to minimize the electrical losses. Now, silicon is extracted from sand, SiO2. You will all know that sand is a very stable product. So to convert it to silicon, we need to go through some pretty aggressive processes. So for example, it involves nasty chemicals such as hydrochloric. It involves heat treatments at temperatures above 1000 degrees C until we finally end up with a silicon wafer that's suitable for a solar panel. So this process, the high temperatures and complicated flow diagram means that the material cost can be quite substantial. To illustrate that, what I have is a breakdown of the individual contributions to what is called the energy payback time. So the energy payback time refers to how long you need to run these devices in order to cover the energy that was put in to produce the device in the first place. So in the case of silicon solar panels, the energy payback time is typically around 1 year, which means that after a 1 year period, then you start producing net electricity. So if we break down the energy payback time, what you see is that the major contributors are this contribution called balance of system. This is typically the inverter that is used to converting DC into an alternating current. But a 50%, another large percent is taken up by the materials cost. So the cost of producing silicon from sand, as well as shaping it into the required wafers. So if we can reduce the material cost, in other words, if we could replace silicon with materials that are more strongly light absorbing, then potentially we have huge energy savings that we can introduce, thus making silicon solar electricity a lot more attractive. Now, these strongly light absorbing materials are what are called thin film materials. And when we explore the type of materials that we can use for devices, we need to consider, amongst other things, this parameter called the band gap. I won't go into the physics of what this means, but you could think of it as the minimum energy of light that the material can absorb. So if we take something like glass, for example, we know that glass is transparent to light. In physics terms, that means it has a large band gap, which means that there is not much light absorption, so the efficiency you get is close to zero. However, if we reduce the band gap, so glass would sit to the right of this diagram, as we gradually reduce the band gap, then the efficiency starts increasing until we hit a sweet spot. So the first step in selecting materials is to find those materials which have band gap in this sweet spot region. And we come up with a number of contenders. So you have cadmium telluride, as well as compounds containing copper indium diselenide and copper gallium diselenide. These materials have actually been commercialized. So First Solar in the US produces CdTe solar panels. These are rivals to the traditional silicon-based solar panels. And companies such as Solar Frontier in Japan and Meosol in the US produce CIGS-based solar panels. New kid on the block is this material called hybrid perovskites, which have also reached very high efficiencies. And the leading company here is Oxford PV, which is a UK-based company. This is what a thin film solar cell looks like under the electron microscope. So you can see that this scale bar is 2 microns. A micrometer is roughly the diameter of a human hair. So you can think of the scale bar as approximately 2 hairs placed side by side. Okay, so this is the material, the thin film material that is responsible for absorbing the sunlight and generating electricity. You can see that it's only a few micrometers. So you have a reduction in the material thickness by a factor of around 100. What's more, these materials are very cheap to produce. They're very fast to produce. So First Solar, who produce cadmium telluride solar cells, they could make a full device in a couple of hours. So it's a very fast process that is cheap and able to produce solar panels on a mass scale. The disadvantage, however, is that if you look at this micrograph, you will see that your light absorbing material is not uniform. You can see that it's got a lot of features. This feature is what we call a grain boundary. These grain boundaries represent defects in the atomic structure. And these defects are unfortunately quite commonplace in thin film solar cell materials and are what is currently limiting their efficiency. So this slide here shows how thin film solar cell materials such as CIGS and CdTe compare with silicon. Silicon, currently the record efficiency at the cell level is roughly around 27%, whereas in the case of thin film technologies, you are at the level of around 23 or 21%. You might think that the difference is negligible, but remember, a silicon solar panel has a lifetime of something like 25 years. So even a 1% improvement in efficiency over 25 years leads to a significant difference. So there are issues in terms of efficiency that is limiting the more widespread adoption of these thin film solar cell materials. But we also have other issues that we need to consider. And this is particularly relevant if we are thinking about scaling the solar installation capacity from the current gigawatt levels to terawatt levels. So terawatt is 1,000,000 kilowatt or 1,000 gigawatts. So if we take cadmium telluride, for example, the solar panels that are being produced by First Solar, cadmium telluride as a compound is stable, but cadmium on its own is toxic. And tellurium is a byproduct of copper mining. So there are issues with the abundance or how much of tellurium that is commercially available. And we have a similar story of abundance when we consider indium. So when we are designing solar materials, what we need to consider are elements that are abundant. So for example, this top half of the graph shows you abundance of the various elements. So a high value is good. We want the materials to be cheap. So this bottom half of the graph is showing the cost. Again, a shorter bar means it is cheaper and more desirable. And we also need to have a high level of production. So again, how many tons a year is being commercially produced. So we can try and optimize, select elements that are abundant, cheap, and are widely available in order to design new solar cell materials. So a promising candidate is this compound called CZTS. It's an alloy of copper, zinc, tin, and sulfur. And if you take these elements one by one, so for example, copper, you will see is abundant in the Earth's crust. It's cheap as well as having a high annual production. So using these abundant, cheap, non-toxic elements, we can produce new materials. They also tend to have geological analogs. So for example, CZTS is what we call kesterite, or in the geological community, ferrokesterite minerals. You can see that is black in color, which is good because it indicates that it's absorbing the light very strongly. So we can make thin film materials out of this. Unfortunately, although it looks promising on the macro scale, when you look into the at the individual atomic scale, then you run into difficulties. So this is work that was done by my colleague, Chair Douglas Halliday, looking at atomic scale defects in this material. What you find in kesterite is that if you deviate away from perfect stoichiometric composition, then you could have various atoms sitting in individual sites within the crystal lattice. So for example, if we take this corner atom labeled 2A, in the ideal structure, this should be a pure copper atom. But what my colleague Douglas Halliday found was that if you move slightly away from this perfect stoichiometry, then instead of having perfect copper occupancy, you could also have intermixing with zinc. And this is a form of defect in the crystal, which leads to electricity losses and lower efficiency. So there's still a lot of work needed to be done to improve the efficiency so that we have a technology that's comparable with silicon. There are other candidate materials. So this is one material that I'm working on. This is a compound of antimony. This is stibnite. The crystal structure of stibnite is interesting because it consists of these 1D ribbons. So unlike your traditional solar cell devices, the charge transport, if you like, is one-dimensional, is taking place along the ribbon direction. And what that means is it provides a pathway to overcome some of the defects such as grain boundaries, because if you imagine that these ribbons are stacked in the vertical direction, then the charge transport is taking place up and down the thin film, and it avoids the deleterious grain boundary regions. So stibnite is one material that is being researched at the small-scale R&D level. Another compound that we're working on is bonanite. This is, again, a mineral-based compound. It's a mineral of copper, lead, antimony sulfide. The nice feature of bonanite is that it is what is called a ferroelectric material. So ferroelectric materials are polar materials, and you can think of it as having both a separation of both a positive and a negative charge, similar to a battery. Okay, so you can think of this material as a small battery that has an internal electric field that is then able to extract the current that is generated from sunlight. Again, research into this material is at a very early stage, but just this year, they have demonstrated a working device with an efficiency of around 2.7%. This is still far below the 20% efficiency of silicon and commercialized thin film solar cells. But nevertheless, these are early days, and certainly these kinds of materials show a lot of promise. So with that, I'd like to summarize. Hopefully, I've shown you that solar PV is competitive with other renewable technologies, but we need to be going a lot faster, which means we need to replace silicon, the current market technology, with alternative materials. These are thin film solar PV. These are currently commercialized. There are companies that are producing thin film solar PV, but the performance is still inferior to silicon. And we still need to do a lot of R&D to understand the internal defects within these materials and mitigate those defects so that we can achieve high efficiency. So with that, I'd like to thank you for your attention.
Well, thank you very much, Budhika, for a fascinating overview of some of the challenges that we face when trying to develop new materials for the next generation of devices. And thank you also for a very nice summary of some of the work that I was doing in the past.